As I promised you, I will today introduce in a nutshell what is a derivative for yani ddx of a function of x, and then we'll in the same way I'll try to explain what is integral dx of a function of x, any function of x. So these two things we need in the what I promised, that I will derive the equations, the mythical equations which I write here for reference. V is equal to u plus at, the first equation of motion, under the constant that a is constant, and s equal to x minus x naught is equal to ut plus half at square. These two equations I said that I'll derive it using the principles of calculus of derivatives. The differentiation and the integration. So for that I have taken on an xy graph where y is a function of x as x changes. So the graph shows as to how the function is changing with x. I have purposely taken a function wherein first of all from the zero value it is increasing like this, and then after achieving a peak it decreases. This could be one of the mathematical functions. It I have just taken a graphical function to make you understand as to what is the value. To you, with your naked eyes, it appears that initially the function is linear, then it becomes kind of non-linear, and then it peaks here and then it decreases, and well, there is a kind of a curvature. The curvature which is very prominent over here, but in the tidbits as the value of x is increased, this curvature changes. So now let's take a certain portion of this graph, and I'll just use my fingers to decrease, to erase this part, and just say that let us have these 2 points, which is x and which is x plus delta x as the value of x changes. So I can now see, and we can see that this is a kind of because the value of delta x is small, so what I get is a right angle triangle where this is delta x and this is delta y. Appears to be a straight line over here, but even if you can see a curvature over here, what I can do is I can reduce the value of delta x to such an extent that this definitely becomes a right angle triangle. Then, now for example, I will do the same exercise here. As the value of x is changed from x to x plus delta x, the value of y changes from y to y plus delta y. I can show to you by taking the same value over here. You can see that the value of delta x is the same, but the value of delta y is a lot less than the value of delta y that was there. Delta y and delta x. Now delta y upon delta x is the rate of change of y with respect to x, which appears to be in this case to be larger because the value of delta y is more than the value of delta y over here. So it indicates the slopes that we obtain is still the slope here and here. In both the cases the slope is positive. Now I take a similar change in the value of delta x and take these 2 points, where in between these 2 points the value of delta x is again the same, but the value of delta y, which was increasing in this case, increasing in this case, now has decreased in this case. So the value of delta y is kind of negative. Of course, I'll draw this and still obtain a right angle triangle. So here the delta y upon delta x, delta y here and delta x here. Here the case of if I write dy dx in the first instant, second instant, third instant, let me say that this is the first, this is the second, and this is the third thing that we are discussing right now. So from the curve dy dx, rate of change of y with respect to x, for the case 1, this is greater than 0, and anything which is greater than 0 is therefore positive. In this case also the same thing follows. Dy or dx, in the case of 2, this is also positive. The same result. But here the dy dx, in the third case, in case number 3, this is less than 0 and therefore negative. Here I would like to just remind you what is the difference between a positive value and a negative value. A positive value becomes a negative value, or a negative value becomes a positive value only if it crosses 0. So there the importance of 0 is, and let us try to see as to at what point and where the slope is equal to 0, dy or dx. So this point I am just writing as point number 4. I will not draw, point number 4, and maybe the point number 4, the value of delta y is equal to 0 here. There will be delta y is equal to 0 under the limit that delta x tends to 0, which is not equal to 0, which is finite. This is 0, and therefore the slope over here at the top of this curve will be equal to 0. interesting. If allow me to extend this curve, this value of, if allow me to extend this curve here, then what happens is that again there is a point number 5 here. There is a point number 5 here corresponding to which the value of the derivative dy over dx, here again it is equal to 0. So I'll just write dy dx is equal to 0, as here that dy dx is equal to 0. dy dx is equal to 0. Now in the curve that we have, in the function that we have, a function which is changing like this, where it has changed the value from going increasing to decreasing. Between that I said that there is 0, and here it was decreasing and then suddenly it started increasing. So at this point number 5 also the value of the derivative is equal to 0. This is a location what we call the maximum value, and this is a location which we call the minimum value. So if there are functions, if we map those functions for all values of x, then we will get some maxima and some minima, some peaks and some valleys. For the peaks, also the valleys, the value of the dy dx is equal to 0. So this is what it means to understand dy dx. Now for right now, as I did before also, I'll give you a certain value of fx. Let the function of x be equal to be precise, just for example, x to the power of n. No constraints I have taken. I am just taking the value of this function as this. Then it is found. I can demonstrate sometime if it is required, but right now I know that for all the students it may be easy to understand that dy x to the power of n is equal to n x to the power of n minus 1. This is one of the formulae that we'll use in obtaining these equations from the basic fundamentals or basic definitions of the quantities. Now, suppose this is the process of differentiation, where I've cut this graph into small slices, which I can say, for example, like a butcher uses his knife to make keema. Okay, so I make a keema of this curve at equal intervals of x, and I find that what is the value of delta y upon delta x, yani dy over dx could be positive, could be negative, and if it is to be a continuous curve like it appears to be for any given function, then this has to have a 0 value of dy dx, which number 4 or number 5 shows that this is the top of the curve, and this is the bottom of the curve. Okay, so this represents a maximum, that represents a minimum, and when the occasion comes I'll tell you how to find out, because the value of 0 you obtain by dy dx. So you can say this is the maximum, or you can say minimum, so you have to distinguish between the two of them, whether it is maximum or minimum, which we together call the extremum. Then we have to go for another differentiation, yani ddx of dy dx, and find out if the value is positive or negative, and then say this is maximum or this is minimum. This is how the mathematics is introduced. So for now, I'll be using this formula, which I'm not deriving. I can derive it, but it will take time, so I don't want to waste your time. But I want you to find out how this formula is derived. Easy, it's not difficult at all. But I have to say something. Like I've said, it can be easily shown. Okay? That means whenever we say, the teachers, that it can be easily shown, it means it is sort of difficult. Okay? So anyway, I'll say that it can be easily shown, and okay, because I've said it and because you are now smiling, so I'll just say that suppose there is a function which I say that, just one example, I used it also in the last lecture, that there is a function x squared and I want the ddx of x squared. So what is that? This is equal to y plus delta y minus y upon delta x, to be short. You understand what I mean. Okay, so for y I'll write, this is y plus delta y, so this is equal to x plus delta x whole square minus x square upon delta x, and the condition is again the same, that delta x tends to 0, is very, very small. So if I open, so here y is equal to x square, as I have taken here, y is equal to x square. So first of all I will write this, that limit delta x tends to 0, I will write the equation like this and substitute the value of y plus delta y, which is x plus delta x whole square minus y, which is equal to x square, and again the same limit I put here, delta x tends to 0. And let me expand. So this is x square plus 2x delta x plus delta x whole square minus x square divided by delta x. For example, limit, of course, delta x tends to 0. So you can see I can cancel out this with this and divide these two terms by delta x. So this turns out to be equal to limit delta x tends to 0, and the first term is 2x plus second term becomes delta x. Okay. Now let us apply the limit. When we apply the limit, delta x tends to 0, so I can write this as equal to 2x. This equal to 2x. So my value here turns out to be equal to ddx upon of x square ddx of x square is equal to, now this, the power, this turns out to be power into x to the power of, I can write 2 minus 1, which is equal to 2x to the power 1, which is equal to 2x. The condition is that the change is infinitesimally small. In that case, this is what is obtained. So for any other case, for example, x to the power of n, the power here, the index over here, n and x to the power of n minus 1. This is the formula that we'll be using in the differentiation process. So similarly, you can say that ddx of x cube is equal to x plus delta x whole cube minus x cube, and that will also turn out to be equal to x cube plus 3x square x plus 3x square x plus 3x delta x square plus delta x cube minus delta x cube. And then again you can see you will get the values, this x to the power of 3 and x to the power of 3 will cancel out, okay, and when we divide it by 3, I'll get 3x square plus 3x delta x square plus, delta x plus delta x square. And naturally, when I put the value of delta x as equal to 0, then these terms, they vanish, they become vanishingly small, and what is left is 3x square. So similarly, for any value I have ddx of, I'm sorry, why didn't you tell me, Mr. Nabil, that this is ddx of x to the power of n. So ddx of x to the power of n or ddx of y, if y is equal to x to the power of n, it will turn out to be n x to the power of n minus 1. So this is one relation that I am going to use, but before that, maybe I end this lecture here. After that, I will tell you what is the understanding of an integration is. What means integration? So this is differentiation, and then I am going to tell you what is integration. And for that also I say that let there be any function of x, any function, doesn't matter, function 1 or function 2 or whatever, y is a function of x. And suppose, now this time I am taking a function which has a finite value. It ends up here that this is a limit of x2 and this is another limit x1. Now I want to know as to what is the total, in other words, yani area between the limits this and this. It could be with limits, certain limits, it could be indefinite. Okay. So between these two values of x is equal to x1 and x is equal to x2, I want to know as to how much area. Area will be in the units of x and the unit of fx multiplied by the unit of fx. So it doesn't matter. But I'll just take here a certain strip and tell you what it means by integration. So I take a strip over here which I have made here, and this value is say the function of x at the given value of x, and in this given value of x I have just made an increment, and this is delta x, or let me write it as dx, which tends to 0. Here it appears to be, to me, to you, to anybody, that this is a slanting line. But if this dx tends to 0, then this slanting line will become a kind of a line parallel to the x-axis. In that case, definitely we can write the area associated with this, the total area over here, because this is a rectangle, so the area will turn out to be equal to fx dx. Area under the curve between the limits x and x plus delta x, for this value over here which I have taken randomly, and area will be equal to the function x or y, whatever, function x into dx. Now, if I want the entire area between x1 and x2, so what we have to do is, we have to take adjacent rectangles which are close to each other, and then from the value of x equal to x1 to the value of x equal to x2, between these limits, and we'll say that the entire area over here, the entire area in entirety, what we are doing? We are adding. What we are doing? We are adding 1, 2nd, 3rd, like that. Okay? So I'm adding and adding and adding and adding. That is, I'm integrating them. That is, I am integrating them together. So I will write this, that the total area within the limits x1 to x2, these values, this is equal to an integral fx dx. Now what I have done? I have added and added and added and added. That is, I have summed up all these infinitesimally small areas, and that is why I was told by somebody that this is actually nothing but this elongated symbol of integration is nothing but summation, because summation is also used as, what is this? What is this? This is sigma. Sigma capital and sigma small, and the sound that is there is basically the same sound as we have S, ya sa, ya seen. So the same sounds are there, but here this has been extended, and this is called integral function of x dx, and then we can put the limits between the limits x1 and x2. So in this case we understand what is summation, what is the integration, and here what is the disintegration, or what is the derivative, or what is dy dx, and this is integral dx of function x. I'll not read it as, mentally you must read that integral dx of function x, not integral fx dx. between the limits x1 and x2. If the limits are not there, then you will have to add a constant which is obtained by the boundary conditions. Okay, so let me introduce to you again straight away the formula of integration for functions like x to the power of n. We say that integral x to the power of n or m or whatever dx is equal to x to the power of n plus 1 divided by n plus 1 plus a constant of integration in the indefinite integral, and therefore in this case of a definite integral, what happens is, because in this case, because that same constant of integration will vanish, so we'll get this as this is equal to the integral. For example, here I'll get x to the power. Before that, I'm sorry. It's very, very, very important condition. And the condition is that here there is a condition that n plus 1 is not equal to 0, or n is not equal to minus 1. So the integration for n to the power of minus 1 has to be derived by other means, but else why? Because if n is equal to minus 1, then this becomes equal to 0, and this is a finite thing divided by 0, which becomes infinite, and we are talking about finite integration. And then now we have a set of two formulae, one for differentiation and the other for the corresponding integration, and I'll just save these two formulae to obtain the equations v is equal to u plus at and s is equal to x minus x0 equal to ut plus half at square, the separation. Okay, and I'll have occasion to explain these things more. This I have done the whole exercise for the sake of those beginners, and particularly biology students who are just given this set of formulae and they remember them, and they are at a loss why these kind of formulae etc. are there. So I'll just write dx to the power of n dx is equal to nx to the power of n minus 1, where n can have any values, and integration x to the power of n dx as equal to x to the power of n plus 1 here, and divided by the same n plus 1 over here, plus a constant of integration which we will have an occasion to obtain the values from the boundary conditions. Of course, under the constraint, the most important constraint, that n plus 1 is not equal to 0, or n is not equal to minus 1. So these two set of formulae we are going to use to obtain these from the from the basic definitions. And what are the basic definitions? The basic definitions are A is equal to dv dt and v is equal to dx d dt of x. So these are two things that we'll use to obtain these equations, this set of equations, from the use of differential and integral calculus. Differential and integral calculus. So in the next lecture I really derive these things, and I hope what I have done today is just introduce you the concept of differentiation and the concept of integration in a nutshell, which will make you feel elated as to today you know about these two very simple exercises in mathematics, which were done by Newton and Leibniz in their peak days, and till now the Britishers, they hero worship Newton, and their German counterparts, they hero worship Leibniz, and they are fighting over it as to who obtained it when. So anyway, that is not the matter. The matter is that if you ponder over it, if you probe into the things in the books of physics, these are given, maybe in the appendices of the chapters, but if you have occasion to for the bio students to interact with your mathematics student counterparts, maybe they will be able to help us to understand what is differentiation and integration. But I will sum it up with a story. That some man who was rather I'll say it in Hindi, Urdu, somebody went to Germany, and when he came back, then he was describing to everybody else that Germans are a great race. Germans are a great race, and everybody asked why. He said, you can see that they have made amazing machines in which they can put in a bull, okay, and the output of the machine is packed meat, packed कीमा, खाल अलग, जूते बने हुए, वगैरह 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 वगैरह। तो जब ये सुनते सुनते वो हो गए, तो एक साहब ने उनसे पूछा कि भाई आप कब आए जर्मनी से? तो वो बोले कि साहब हमें तो आए हुए जर्मनी से जो है वो कोई एक हफ्ता हुआ है, अभी आए हैं। उनका ओहो, फिर तो आपको कुछ पता ही नहीं, यू हैव मिस्ड द बस। उनका क्या हुआ भाई? और लोगों ने कहा भाई आप बताइए आप कब आए? उनका मैं तो अभी दिल्ली से मैं उतर के और जर्मनी से आया हूँ और अपने घर जा रहा हूँ। तो उनका क्या मशीन है? कहने साहब जर्मन्स ने तो कमाल कर दिया। उनका वो सब जो बुल के को इन्होंने मशीन में टुकड़े टुकड़े करके हर चीज़ पैक कर दी थी, और जूते भी बना लिए थे। वो जर्मनों ने अब ये किया है कि वो सारे जूते, वो सारा कीमा, वो सारी बोटियाँ, वो सारी हड्डियाँ, वो सारी चीज़ें एक मशीन में जो है वो इनपुट करते हैं, और जब मशीन को उल्टा घुमाते हैं तो उसमें से डकारता हुआ बुल वापस आ जाता है। सो व्हाट इज दैट डकारता हुआ बुल? दैट डकारता हुआ बुल इज द प्रोसेस ऑफ इंटीग्रेशन, ओके, एंड द फर्स्ट पार्ट ऑफ द फर्स्ट नरेटर is the process of differentiation. So process of differentiation, process of integration are together like that. Of course you can have many big books on differentiation and on integration, many volumes, but for us, हमारे लिए at this stage अभी ये सफाइस करता है। बाद में जब ज़रूरत पड़ेगी तो तो हम डिफरेंशिएशन ऑफ साइन फंक्शंस, कोसाइन फंक्शंस एट्सेट्रा और इंटीग्रेशन ऑफ दोस भी करेंगे. So thank you very much for being with me today, and I hope that I have been able to direct you or just probe you to try and learn more about these things in physics. U, Q, V, A, and therefore I will ask you, do Q and V A. Or you can question your colleagues, your friends, and ask them for the answer. Thank you very much for